Professor Enrique Espinosa. Enrique got his bachelor and master degrees in physics at the University of Barcelona in 1987. And next, he worked as a teacher in high schools and in private companies to start his PhD on experimental electron density studies at the Institute of Science and Materials at Barcelona in collaboration with Laboratory of Crystallography at Nancy, and was supervised by Professor Elise Molins and Claude Lecomte. He defended his PhD in 1994, and then he spent 2 years as a postdoc at Nancy, working under supervision of Claude. He then continued to work in this lab for the next year, and then returned back to Barcelona. And in September 1998, Enrique moved to Dijon to work as a crystallographer in a molecular chemistry laboratory at the university there, where he got a permanent position of associated professor in chemical crystallography in 2002. In 2005, he defended his habilitation there, and next year he left Dijon to move again to Nancy, where he got a permanent position of professor of physics in the laboratory of crystallography at Nancy. In 2011, he got the position of full professor in crystallography in the same laboratory, and served for 10 years as a vice dean of the Faculty of Sciences at Nancy since 2013 to 2023, in charge of science, in fact, physics, chemistry, geological sciences, and mechanics. In research, Enrique is mainly interested in interatomic and intermolecular interactions, focusing on molecular assembly and molecular organization in space within the field of crystal engineering and in the framework of structural properties relationships. He developed his own research in the form of studies of factors influencing hydrogen bonding and sigma hole interactions. And so he uses topological analysis of electron density, of electrostatic potential, and of electron density, as well as topographic analysis of electric field lines in space as main tools of his research. He has published more than 150 papers so far, with more than 10,000 of citations, and the H index 42. And today, Enrique will talk about topological analysis of electrostatic potential in molecular systems. Enrique, the screen is yours.
Okay, so thank you very much, Christophe and Paulina, for this invitation that permits to present our results on this subject, on this topological analysis of the electrostatic potential. The topological analysis of any scalar function is the analysis of its derivatives. It permits to retrieve information that is typically hidden in the scalar function itself. To do that, you need that the scalar function needs to be defined everywhere in the space, as well as its derivatives. Then the topological analysis uses similar kind of concepts from one scalar function to another, such as the zero flux surfaces. As for instance, here you have the electron density distribution, and the gradient vector field permits to undertake a partition of the molecular space thanks to these zero flux surfaces, which are surfaces that are not crossed by the gradient vector field of the scalar function. What is happening, for instance, here for the electron density is also happened for another scalar function, such as the electrostatic potential. Of course, the surfaces are placed in different ways. Of course, the basins enclosed by these surfaces are also different, but the concepts are similar. Also, another similar concepts are what we call the critical points, which are the maximum, the minimum, and the saddle points of the distribution that are characterized by the curvatures of the Hessian metrics of the scalar function. Then, if you want to further characterize the scalar function distribution, then you can calculate properties associated to this scalar function at the critical points, for instance, or you can also calculate integrated properties of the scalar function within the basins. The electrostatic potential is defined by positive and negative contributions of the nuclei and the electron distribution. The first derivative, the gradient of the electrostatic potential, is the negative of the electric field. And the second derivative, which is the Laplacian of the electrostatic potential, is related to the charge distribution through the Poisson's equation. This equation has the contributions of nuclei and the electron density. Out of the nuclear position, the nuclear positions, this contribution vanish, and therefore the electron density out of nuclei is straightforwardly related to the Laplacian of the electrostatic potential, and therefore of the electrostatic potential curvatures after diagonalization of its Hessian matrix. In order to characterize how the gradient vector field of the electrostatic potential, and therefore the electric field lines of molecules are in the space, we have undertaken this analysis for a set of crystal structures here, which you can find neutral anions and cations. For the anion TC&Q, here you have the electrostatic potential plotted, and here you can find the local maxima placed at nuclear positions, and the local minima associated to the lone pairs of the nitrogen atoms in the outer part of the molecule. When you calculate the gradient vector field of the electrostatic potential, you get a complete partition of the space in basins. Here you have also another basin with another zero flux surface here. And these basins can have either nuclei or not, as for instance here. Basins which are enclosed by these zero flux surfaces are regions of the space where the net charge is, strictly speaking, equal to zero, because the electric field lines, the flux of the electric field lines through this surface is by definition zero, because you don't have any electric field line that it is crossing the surface outwards nor inwards, and therefore the net flux is zero. And applying the Gauss theorem to this region of the space, that means that this volume has a zero net charge. In the case of this anion here, you have another zero flux surface surrounding all these basins, indicating that all this part of the space has also a zero net charge. So the net charge of the anion is found outside of this surface. It is found by integration of the electron density in these open basins. So here you have 4 open basins. One, it is here, the other is here, the third and the fourth here. So these basins, they don't have nuclei, and they by integration in these basins, you will find the net charge, the negative net charge of the anion. In the case of cations, also, the partition of the molecular space is complete. However, a difference of the anions, here you have a nucleus in each basin. By definition, cations are not enclosed by external zero flux surfaces because they have a positive net charge, and therefore you cannot find this enclosing surface. So the basins in the outer part of these molecular entities, basins are open, as for instance you can find here or here for the hydrogen atoms. In the case of neutral molecules, the partition again it is complete in the space in basins, and inside of each these basins, you will find a nucleus. So here, for instance, you have a basin which is taking all this region of the space. Here you have another one, and here you have the third one for the water molecule. In the neutral molecules, the electric field lines are describing loops around molecules going from one side to the another side of the molecule, or for instance, from one side here in the case of orthophosphoric acid, from this one side to another side of the molecule. So the net charge of the molecule is zero because if you take an enclosing surface, enclosing all the critical points of the scalar function, that is of all the critical points of the electrostatic potential, this surface will exhibit that the net flux of electric field lines is the same outwards than inwards. So you will get exactly the same quantity of electric field lines going outwards and inwards through this hypothetical surface. The electrostatic potential is typically plotted on molecular surfaces to find nucleophilic and electrophilic regions of molecular regions. Then, if you want to be a little bit more precise, you can try to search for the local minima and maxima on this surface. This surface is typically chosen as the van der Waals surface, but in fact you can choose any other surface. However, these local minima or maxima that you find, for instance, on the van der Waals surface, these sites, they don't correspond to the true electrophilic and nucleophilic sites of the distribution, because electrophilic sites are strictly speaking related to the local maxima of the electrostatic potential, as for instance here, and nucleophilic sites here and here are directly related to the local minima of the electrostatic potential, because they behave as these ones as attractors of positive charge, and these ones are behave as attractors of negative charge. And these sites, they don't correspond to what we typically use in charge density analysis when we plot the electrostatic potential on molecular surfaces. So this picture of the gradient vector field of the electrostatic potential is more precise than that of the plot of the scalar function itself. Not only because you will get these true electrophilic and nucleophilic sites of the distribution, but also because you, from the topographic field lines, you will see the extension of the influence of these electrophilic and nucleophilic sites. For instance, for the same molecule, the phosphoric acid, for the same electric field lines that you have seen just before, you can characterize the influence zone of the electrophilic sites. Here you have two electrophilic sites in the outer part of the molecule. The influence zone is defined by the volume which is covered by the field lines that are starting at the same electrophilic site. So here you have two influence zones for two electrophilic sites. This partition of the space is equivalent to a partition of electrostatic basins which are associated to 3-3 critical points. For the same molecule, the same electric field lines, you can also characterize the influence zones of the nucleophilic sites. So here you have two nucleophilic sites associated to the lone pairs of the oxygen atoms. They also exhibit in the outer part of the molecule, and the influence zone of these nucleophilic sites these influence zones are defined as the volumes covered by the field lines that are ending at the same nucleophilic site. This partition of the space in two, for this example, is equivalent to a partition of the electrostatic basins associated to 3+3 critical points. In fact, for the same molecule, for the same electric field lines, you have all the electrophilic and nucleophilic sites influence zones at the same time. And when you do the intersection of all this information, what you get is what we call the primary bundles. So a primary bundle is the region of the space that it is covered by the electric field lines starting at the same electrophilic site and ending at the same nucleophilic site. So in that case, the intersection of these two electrophilic and nucleophilic influence zones is giving rise to 4 primary bundles, 1, 2, 3, 4. Each it is associated to a pair of electrophilic and nucleophilic sites. So each point outside a neutral molecule, for instance here, is upon the influence zone of one electrophilic and one nucleophilic site at the same time. This has some consequence when this molecule lets to feel its electrostatic influence in its neighborhood. Another molecule in the surroundings will interact with a pair of electrophilic and nucleophilic sites, or with another pair of electrophilic and nucleophilic sites, depending of the relative orientation between these two molecules. So depending of the approach of the molecules, the electrostatic interactions will not take place in the same way, because the pair of electrophilic and nucleophilic sites will be different. Another interesting case is when you have nucleophilic groups, for instance, a carboxylate group here, within a cation, L-histidinium, or when you have an electrophilic group, for instance, this hydrogen atom, within an anion. In that cases, nucleophilic or electrophilic influence zones in cations and anions are very well defined by these zero flux surfaces. These influence zones are finite and limited by this zero flux surface, on which, here you have another zero flux surface, on which saddle points appear. Here you have one, here you have another one. So they are 3+1 or 3-1 critical points appearing on this surface, where the electrostatic potential is either a minimum or a maximum on that surface. These saddle points mark the most favorable directions for an electrophilic or a nucleophilic attack. And this direction is the electric field line that it is coming from it's coming from the infinity towards this point here, like that, or the electric field line that is going from this point towards infinity. These electrophilic or nucleophilic interactions or attack can be obtained if the cationic entity in that case, which is pushed away by these electric field lines, is able to climb the energetic barrier that is related to the electrostatic potential value at this saddle point. or in that case, if you have another anionic entity that wants to interact with this hydrogen atom, then this entity has to climb the energetic barrier that it is related to the electrostatic potential at this critical point. In that case, these entities that at long distances are pushed away, they will be able to get into the influence zone of either the nucleophilic or the electrophilic groups, and therefore the electrophilic-nucleophilic interaction will take place. Up to here, I talk about isolated isolated molecules. What about the assembly of molecules? For talking about that, I choose this hydrogen bonding interaction. This is a complex assembled by a hydrogen bond, an H hydrogen bond, and for which I represent here the gradient vector field of the electron density, which is leading to the zero flux surface of the electron density, and therefore the basins, the atomic basins. And also the gradient vector field of the electrostatic potential, giving rise to closed or open electrostatic regions. Closed basins are, as I said before, electrostatic regions where the net charge of the region is strictly speaking equal to 0 by applying the Gauss theorem, because the net flux of electric field lines is strictly speaking 0 in that case, or in that case, or in that case. Open basins, as for instance here, are mainly related to the interaction of the system with its environment. In that case, for instance, you have a neutral complex. So if you put a zero flux surface, sorry, a closing surface around this complex, the number of electric field lines going outwards is exactly the same that going inwards, and therefore the net charge of the complex is 0. At the same time, what you can see is the typical topography of electric field lines of a dipole, okay, flowing from one side to another side of the system. And in fact, this complex has a dipole moment of 3 device. But what are the electrostatics in the hydrogen bonding region? That is in that region of the space, and here it is in that region of the space. So for doing that, we have done, it is the intersection of both gradient vector fields, which are here, where you can see almost nothing. So in order to simplify the picture, here you have the one-dimensional plot of the electrostatic potential. It is the solid line, and the electron density. This is the shaded line along the nitrogen-hydrogen internuclear region for both of them. The minimum of the electrostatic potential marks the position of the zero flux surface of the electrostatic potential, and the minimum of the electron density marks the zero flux surface of the electron density. So the nitrogen atom is taking the region from its nucleus to this zero flux surface of the electron density, and the hydrogen atom is taking the rest of the region. In the case of the electrostatic potential, the zero flux surface is indicating, as far as the nitrogen nucleus is surrounded, is enclosed by a zero flux surface, that means that in region 1, you have a zero net charge. Similarly, the addition of regions 2 and 3 will have also a zero net charge. As far as in region 2, you have only electrons, mainly corresponding to the lone pair of the nitrogen atom. That means that here you have a negative net charge, and therefore, In region 3, corresponding to the hydrogen atom, you have the counterpart balancing exactly the negative charge here with a positive charge associated to the hydrogen atom. So the electrostatic interaction in the hydrogen bonding region mainly involves these regions 2 and 3. Region 2 is around 13–14% of the total distance. This dimension is 13–14% of the internuclear distance in the hydrogen bonding region. This is the same that has been obtained. That have obtained for a set of NH hydrogen bonding interactions. And for this set of interactions, what you observe here, this is the distances from the critical point associated to the zero flux surface of the electron density to the nitrogen nucleus here, and here it is the distance from this critical point associated to the zero flux surface of the electrostatic potential to the hydrogen nucleus here. And the difference, so this region, it is almost the same. In fact, this difference is almost the same for the 21s, and this corresponds to 13–14% of the total hydrogen bond distance. For the same set of hydrogen bond interactions, we have also calculated the curvatures of the electrostatic potential at both critical points, that of the electrostatic potential and the electron density. These curvatures are represented here by squares. Here, this is the positive, and this 2 is for the negative, or the perpendicular one. You have two perpendicular curvatures because of the symmetry of the systems. Both are the same. And white symbols concern the positions of the curvatures at the position of the critical point of the electron density. Dark squares correspond to those of at the position of the critical point of the electrostatic potential. For the positive, for the parallel, and the negative, the perpendicular curvatures. For all these 20 points, these data sets have been fitted against exponential functions, and here you have this solid line. This is the fitting function for the parallel curvature at the electrostatic potential critical point, and this is the dotted line correspond to the same curvature but at the critical point of the electron density, and similarly for the perpendicular one. In the same picture, you have also in circles the values of the 4p rho values obtained at both critical points, and the curves that you are observing here, they are the curves obtained from the fittings of these curvatures and using equation 2. This fitting function obtained driven by the addition of these contributions is what you observe here. And if you do the fitting of this data by using an exponential function for the electron density, this function matches exactly the same in the same way along the whole range of interactions, the curve obtained from equation 2. Okay, so this, in conclusion of that means that the electron density has an effective deconvolution in positive and negative contributions obtained from the curvatures of the electrostatic potential, and therefore that means that at each point the electron density can be know how this scalar function is built from electrostatics. Okay. when you look at phosphates in the crystal structures, you will observe that it's very common to find that phosphates are very close together in the crystal structures. They are linked by hydrogen bonding interactions, where the hydrogen oxygen distance is quite short. It's 1.57. This is the hydrogen atom has been obtained the position of the hydrogen atom from neutron diffraction. That means that interanionic hydrogen bonds between phosphates is a quite paradoxical situation, because this is not what we expect. You have here two negative charges which are very close to each other, where in principle you should expect that a segregation of this negative charge in the crystal structure, but not so close and not linked to each other. So in order to understand this paradoxical situation, we have investigated dimers of phosphates. 7 complexes in gas phase has been calculated, exhibiting a different number of hydrogen bonding interactions between 2 and 4 with different kind of conformations. For all of them, we have used the phosphorus distance as a reaction coordinate, and we have calculated their interaction energies step by step by optimizing the rest of interactions once we have fixed each phosphorus distance. And this has been done for the seven systems. In all of them, the interaction energy rises in its positive value due to this Coulombic repulsion between the negative charges. And in all cases, we observe that all of them rises and they reach a local maximum in all cases, from which, if you continue to decrease the distance, so you approach more the moieties, the systems are falling down in their positive energy, reaching an equilibrium geometry in all of them. In an equilibrium geometry, you have a local minimum, and if you continue still decrease the phosphorus distance, all of them change in conformation, because all the systems are optimized at each step, change in conformation, and all of them reach the more stabilized system, which is this one, falling into this energetic profile of this system. In fact, this interaction energy at this equilibrium geometry is positive, indicating that the system, even if it has been fall in a potential wall depth, is destabilized. So here the energy is quite high, is positive and quite high, more than 100 kilojoules per mole. In fact, if you want to dissociate the system needs to climb this energetic barrier, that it is about 70 kilojoules per mole in order to dissociate, in order to reach this transition state, and from which the restoring forces are not able to restore this equilibrium geometry. In order to trying to understand how things are in this situation, we have here represented for the most stable system, this dimer in that plane. We have represented the gradient vector field of the electrostatic potential, and on which we have superimposed the atomic basing of the acceptor atom. And what we observe is that the oxygen atom, here represented in gray, is within the electrophilic influence zone of the hydrogen nuclei. So here, what's happening is that the oxygen is well inside this region, this electrophilic influence region, from which I talked about some slides before. if you look at the position of the zero flux surfaces of the electron density, which is this one, and the electrostatic potential that it is this one, here you have a zero flux surface of the electrostatic potential. So here you have this intermediate region between these two zero flux surfaces, and the electric field lines that are crossing this region are electric field lines that are pulling electrons towards this nucleus, this hydrogen nucleus. And this is the attractive electrostatic attractive local electrostatic attractive forces that are able to compensate for the Coulombic repulsion, and these are the electrostatic forces that are able to make this the restoring forces when the system tries to separate both moieties. These restoring forces are able to retrieve this equilibrium position. So this is what's happening, and this region, this intermediate region, is what we call the electrostatic attraction region. If you compare the phosphate complex to the neutral phosphoric acid complex, and you plot the gradient vector field of this system, you will observe that, in fact, in the hydrogen bonding region, things are very similar. Electrostatics are very similar in the hydrogen bonding region. You will find this electrostatic attraction region, which is very similar to this one. You will see also the electric field lines that are pulling electrons toward the nuclei. In both cases, what it is the main difference observed is coming from the outer part of the molecules. And here, this outer part is represented by the electric field lines in these dashed lines, dashed blue lines, which are representing this Coulombic repulsion. They are the electrostatic forces that are pointing towards infinity. They are pushing electrons towards infinity. So in this intermediate region between the zero flux surface of the electrostatic potential and the zero flux surface of the electron density, these electrons that are here are pushed towards infinity, and this is the representation of this Coulombic repulsion in terms of the electric field lines. If you compare the gas phase complex to the same complex, but embedded in a polar environment, for instance, in water, you will see that polar environments effectively screen all the electrostatic interactions and therefore modify significantly the energetic profile. The energetic profile actually with the PCM model with water falls into a very negative value at the equilibrium geometry. So the difference between both cases is more than 200 kilojoules per mole, in addition to remove, in fact, this energetic barrier, no energetic barrier. So what does it mean? Does it mean that once the system is formed in gas phase, which is the most defavorable case, the complex will remain stable under changes in the environment. We have generalized that with a big family of oxoanions, for which we have the anionic forms, but also the protic forms and the salt complexes. For two of them, here you have, the protic systems, the anionic systems, and the salt systems. Cohesion forces in all of them, the cohesion forces are mainly in the hydrogen bonding regions. It is again in these, they are the electric field lines that are crossing this intermediate region between the zero flux surfaces of the electrostatic potential and the electron density in all cases, for the protic complexes, for the anions, and also for the salt complexes. The difference is that these cohesion forces have also a contribution, an external contribution, not necessarily in the hydrogen bonding region. Sometimes you find that some electric field lines are flowing from one moiety to the another molecule through the space. This is not observed in the anionic complexes, but this is observed in the protic ones and in the salt complexes also. Here you have also the electric field lines that are flowing from one side to another side, from one side to another side. Local electrostatic forces in hydrogen bonds are similar, so you will have this electrostatic attraction region. You will find that aggregates are very similar in their these regions and also in the electric field lines within crossing these regions. And because of that, the conclusion is the hydrogen bonds do not depend on the charge of the complex. So what is happening in the hydrogen bonding interaction is mainly independent of the charge of the complex. The electric fields in anions here, it is what is the main difference? It is related to these dashed green lines. This is what I tell you just before. They are covering the anions, and these force lines are pushing away electrons. So here you have an electrostatic force that it is trying to put electrons in that way, in that way, in that way. If you do for a one moiety the net resultant force, this net resultant force will take this direction, and for here this direction, and these are these resultant forces are trying to separate both moieties. They are compensated by these local attractive interactions in the hydrogen bonding regions, and it is thanks to these local electrostatic interactions that we can observe, in fact, the anionic aggregates. The energetic profiles in the anionic for all these anionic derivatives are here. For one of them in gray. Here, what we observe it is that for all of them, behave as a punctual charge interaction. So this is the most simplest, the simplest model that you can build for two anions. And in all cases, for all these anionic complexes, in the dissociation in their resociation regions, they behave as two punctual charge, in fact, from their energetic profile. So we have tried to see how the electric field lines evolve from this equilibrium geometry to this transition geometry. So this is the complex at the equilibrium geometry, where you can find here this electrostatic attraction region, here, the electric field lines. And in the position at the geometry of this transition state, what you find is the electrostatic attraction region remains in place. However, is farther from the hydrogen nucleus than at the equilibrium position. And also, what we observe is that the electric field lines you have a less density of electric field lines crossing this shaded region. That means that the local electrostatic forces are weakened, and it is because of that that at this situation, at this geometry, the electrostatics, these local electrostatic attractive forces are just able to restore the equilibrium geometry, but for a longer geometry, they not be able to restore this equilibrium geometry, because they are not able to overcome this repulsion, this Coulombic repulsion. Okay, what we have observed with the anion-anion interactions, we observe also the same kind of things with cation complexes. This has been analyzed in the case of nucleic acids interactions in Watson-Crick disposition. So here you have the neutral monoprotonated and deprotonated complexes with uracil and adenine, guanine and cytosine. Here, adenine is protonated at position 3, so here the proton is there. Here, guanine is protonated at position 7, so here. And here, the complex has been also protonated at uracil and for O4 at this position, and here for O2 at this position. Okay, so what we observe is that in neutral, monoprotonated, and deprotonated complexes, the situation is very similar in hydrogen bonding regions, and here you have the 3 hydrogen bonding interactions. This is very similar for all of them. When you compare these cationic systems to the previous anionic complexes, the situation is also similar. Acceptors, the acceptors of the hydrogen bonds need to be placed well inside the influence zone of the hydrogen nuclei in order to get this assembly for the system. The cohesion of the complexes, we observe also the cohesion of the complexes, a contribution to the cohesion of the complexes also outside of hydrogen bonding regions, mainly in neutral, but also in monoprotonated systems. For instance, here you can see how these electric field lines are flowing from one moiety to the another one, from one moiety to another one, from one moiety to another one. So here you have some contributions also outside the hydrogen bonding regions. Two interesting things that we have found in these systems is when you try to protonate the NH2 group in either adenine, guanine, cytosine, or the protonated adenine in position 3 or guanine in position 7. In fact, when you see the electric field lines going from a nitrogen atom, a nitrogen nucleus, from the position of the lone pair of an oxygen atom here, or you can see the same here, or here, or here, or here. If you try to protonate, for instance, this nitrogen atom, when you optimize the system, the hydrogen atom is not anymore bonded to this nitrogen. Is transferred to the position of the initial lone pair of this oxygen atom just here. In fact, this is what is happening with this system. When we have tried to protonate here this nitrogen atom, the hydrogen, the proton, has been transferred to this position, and it is what we observe here. So the electric field lines, they are also indicating that a proton, okay, so will feel the pushing force of these electric field lines. They are pushing they are pushing positive charge, whereas this is trying to pull positive charge. So the proton is pushed by this nitrogen nucleus, and it is pulled by this lone pair of this oxygen atom at the same time. Also, another interesting thing is intramolecular effects. For instance, in this complex, here you can see a significant electrostatic interaction between this hydrogen nucleus and this lone pair of this oxygen atom. In fact, that it is weakening this hydrogen bonding interaction when you compare, for instance, once the adenine has been protonated at position 3. In that case, we see that this influence is much lesser than here. And in that case, the hydrogen bond it is stronger than this one. So also the electric field lines outside the molecular system, they are also indicating electrostatic intramolecular effects associated to the assembly of molecules. Okay, so to finish, we have, I will finish in quickly. To finish here, an analysis that we have done, taking all together, that means neutral, positively charged and negatively charged systems, cationic and anionic, all together with the same kind of system. For doing that, here you have the different derivatives that permits to get either neutral or dicationic or dianionic systems, on which we have also varied the length of the chain that permits to put closer or at a longer distance the charge in the cationic or in the anionic system. Okay, what we observe from the electric field maps, that the neutral systems, these two neutral systems with a length of 1 and 2, 1, they are very similar to each other, but they are also very similar to those of the cationic system and those of the anionic system. So in fact, charge in the hydrogen bonding regions, charge does not affect so much. In fact, what is happening in hydrogen bonding region, and this is observed from the electrostatic effects from the electric field lines. The dissociation profiles for the cationic systems with the different lengths, 1, 2, 3, 4, and for the anionic systems for the different lengths are represented here. So we observe here the energetic profiles for all these systems, and in red, this is the most simpler system. This is a two positive charge interaction or two negative charge interaction. So what we observe that it is here, it is the energetic profiles seems to be roughly the sum of two contributions, one which is related to the hydrogen bond, what is happening within the hydrogen bond region, and the other one which is representing the Coulombic repulsion. This is the simplest way that you can do. This is a very roughly modification, a very roughly way to take into account this this Coulombic repulsion. In fact, if you if in the dissociation profiles you remove the Coulombic repulsion for the cationic systems and for the anionic systems, and you remove this charge contribution, what you get is a profile that it is very similar to the neutral ones for the same lengths. So it is very similar in the cases of the cationic system, but also for the anionic systems. So that means that, in conclusion, that the removing the Coulombic repulsion from these charged complexes, even in a very roughly way, because this is just two punctual charge, what remains in the energetic profile is very similar to a neutral complex, and this is quite interesting because systems, charger systems, they don't affect so much the assembly, the assembly of the molecules. Okay, in conclusions, so zero flux surfaces permits to undertake a partition of the molecular space in electrostatic regions. Closed regions are related to a zero net charge, whereas open regions can be either with a positive net charge if they have nuclei, or negative net charge if they don't have nuclei. In crystals, you will get only this case, okay, because everything you have in all directions of the space, you have a closed basins. Electric field lines are defined as the negative of the gradient vector field of the electrostatic potential, and they are the force lines. They are the electrostatic communication between molecules. In molecular recognitions, they are driving the orientation of the relative orientation of molecules by facing electrophilic and nucleophilic sites in different molecules, and this is driving not only the orientation but also the approach of the molecules, and at the final stage, the assembly of the molecules. The influence zones of electrophilic and nucleophilic sites in molecules permit to understand electrostatics in the outer part of molecules. This is much more informative than the scalar function plot itself on molecular surfaces. They permit not only to work with the true electrophilic and nucleophilic sites, but also with the extension of their influence in the space. And finally, the combination of the topological analysis of the electrostatic potential and the electron density permit to identify these intermediate regions in the space, intermediate between these zero flux surfaces of both scalar functions that are directly related or associated to an electrostatic attractive interaction in the assembly of molecules. Okay, so I would like to acknowledge, sorry for it took a lot of time. I would like to acknowledge Professor Ivonne Alcorta, Professor Elias Molins, and in particular Ignasi Mata for all this work that we have carried out during the years on the topological analysis of the electrostatic potential. And of course, I thank you for your kind attention.
And thank you, Enrique, for your excellent lecture, which is now open for questions and comments. If you have some, please put them on chat.
So maybe I can ask in meantime.
Yes, please.
Yeah. So for charged molecules, if they are far away from each other, and if they are of the same charge, so there has to be some. If they are far away, there has to be some external force which brings them together, and then at some certain distance, they will attract each other, even if that force disappears. It's what actually
the force, the repulsion does not disappears. The repulsion is always there, in fact. However, if the molecules are being close together because you give the enough energy to climb this energetic barrier that it is necessary to climb in order to get into the influence zone of, for instance, electrophilic or a nucleophilic group, then the electrophilic nucleophilic interaction will take place. And this is needed at very close distances, in fact, very close geometries, because this influence zone, as I will take this, here. You need to be here or here, okay? In that case, if you have, for instance, you have two cations, okay? But you have, in a cation, you have a hydrogen that wants to interact with this carboxyl. When you look at the geometry, the equilibrium geometry for an ion-anion interaction, for instance, in the phosphates, I didn't talk about that, but if you look at this distance, this equilibrium distance, this is shorter than this one. This is shorter than this one. And if you look at the distance, the equilibrium distance in the neutral complex, this is longer than this one. And here you need a very short distance because you need that the electrophilic, the acceptor needs to be inside, well inside into the electrophilic region, the electrophilic influence zone. So electrostatics everything are there, local attractive, but also the repulsive. The repulsive are there, and you can see that because the energetic profile is positive everywhere. The energetic profile is positive everywhere at any distance, and it is very positive. In fact, here you have a more than 100 kilojoules per mole. So this is very destabilizing from the energetic point of view. But the forces, the local forces, between the nucleophilic and electrophilic interactions are able to restore this equilibrium geometry.
Basically, once you force those molecules to be close to each other, they will stay.
Yeah. So for doing that, what you can do is to put a solvent. Okay. Yeah. So if you use a solvent, this is what is happening. You put a solvent, and then, okay, so you are screening, polar solvents are screening all the electrostatics all. So the attractive and the repulsive. But as far as the repulsive are so important, so this negative repulsion is much more, has a contribution which is much more important than the local one. Because of that, the final equilibrium geometry with a solvent, it is negative in the interaction energy. So here you have 200 kilojoules per mole difference between this situation and this situation. So the solvent is able to stabilize, and actually the interaction is stabilized because the interaction energy is negative, and you don't have this barrier. This barrier has disappeared. Okay. At the same time, you have also screened the attractive electrostatic forces, and it is because of that this geometry is longer than this one, because you have also weakened the electrostatic force, the attractive electrostatic forces in the hydrogen bonding region.
Mm-hmm. We have a question or comment from Hans-Bert Birgi. What about calling this kinetic stabilization?
The kinetic stabilization. I don't understand very well the question.
So it might be like it's another word. It's metastable, because the system on the left is somehow metastable, right?
Yes. Yeah. So in fact, if you separate, in fact, in two regions, okay, from here, this is the dissociation region, which is the system on which the system behaves as a two-point dual charges. Okay, so you have two anions. Okay, you have phosphates, but in fact, from this distance to longer ones, this decreasing, okay, or this increasing if you are coming from long distance to shorter distances, it is like two-point dual charge. That from the energetic point of view, that behaves as here. This is two-point dual charges. Okay, so for all these systems, all of them behave as two-point dual charges at longer distance. At shorter distances, these electrophilic and nucleophilic sites still start to feel their action in such a way that the electric field lines are able to restore the equilibrium geometry, that is this one, because they overcome the Coulombic repulsion. And even if the Coulombic repulsion that it is observed here it is the Coulombic repulsion, it is observed in all these electric field lines that are trying to pushing away the electron distribution on this part, on this region of the space, in between these two zero flux surfaces. The resultant force of all that, it's a resultant force in that direction. Is in that direction. Here it is the same for this moiety. It is in that direction. So these resultant forces are trying to separate, but these attractive forces here are able to restore this equilibrium situation, even if the system is destabilized, because the total energy is positive. It is very positive. It is more than 100 kilojoules per mole. Mm-hmm. But the restoring forces are able to retrieve this equilibrium geometry. However, if the system is at the transition state, here, this is the situation of the transition state, the comparison of this situation with respect to this situation is that here you have a density of electric field lines that has decreased, significantly decreased with respect to that. The region still remains. This region between both zero flux surfaces still remains, but the electric field lines that are pulling electrons towards this electrophilic site has decreased. And this is because of that here the system is just at the limit between the situation or whether the system is able to retrieve the equilibrium states, because the restoring forces will push the system towards this geometry, or if the system is at a little bit longer distance than this transition state, so the restoring forces are not able to restore, and therefore the system will separate. You will have the dissociation, because all these the resultant force of the Coulombic forces along that direction and along that direction overcome, in fact, this attractive interaction. I don't know if this answered the question.
Hans Bet can unmute. You can unmute your mic and camera and ask further questions if you want to.
So this is somehow similar situation to when you have different kind of polymorphic systems, and even if one is not like from the thermodynamical point of view stable at the particular conditions, you can, by some extra energy, by kinetic movement of molecules, you can reach that local minima. So this is maybe why Hans called it kinetic kind of stabilization.
Yes, in fact, you can, from the energetic point of view, you can have a system, a destabilized system, because the total energy is positive. However, the system can fall into a potential well depth in some situations. This is the case of hydrogen bonds in these anion-anion interactions, for instance. But effectively, you can work with another kind of systems that the interaction energy is positive, and therefore the system is destabilized. So from the energetic point of view, the system should not form. However, if you found conditions that are able to create, in fact, this transition state, because the transition state, in fact, is the consequence, as you will find here, a local minimum. Okay, so this is a consequence of this local minimum. In fact, you cannot find that without finding this local minimum, because the function is a continuum function. Under upon several kind of conditions, you can obtain effectively in different polymorphs, you can maybe find situations like that.
Yeah, no doubt that electrostatic potential is allowing for incredibly detailed studies of interactions. I recall some old papers by Pulitzer and Murray who introduced some parameters characterizing electrostatic potential either locally or globally. Do you think that that you could propose like some new parameters which could be, I don't know, correlated with some bulk properties of interacting, say, molecules, or in general bulk properties of materials?
Yes, in fact, we have a paper on which we develop an electrostatic descriptor associated to the monomer that permits to understand when this monomer associates to another molecule, it makes an assembly. Okay, and this is related, in fact, to the position of specific points of the electrostatic potential and electric field. Yeah. In fact, the signature of the electrostatics is, of course, is in the electrostatic potential. But my message here is that when you look at the electrostatic potential only, some of these informations are hidden. It's like when you look at the total electron density. Okay, you look at the total electron density and you cannot see, for instance, lone pairs. Okay, but with other scalar functions, it's the same. If you want to extract a maximum of information from the function, I think a very good strategy is to do a topological analysis. If the function is defined everywhere in the space and their derivatives are also defined everywhere in the space. You apply the topology and then you will have a rich quantity of information that it is increasing your knowledge of the scalar function itself.
Yeah, so the dream would be to have such electrostatic potential for binding centers in proteins, for example. Then you can understand how ligands are.
Yes, yeah. In fact,
them.
yes, you are completely right. So I'm working with Benoit Guillot, and a PhD thesis will be defended, I think, in September. Which in this PhD thesis, this kind of problematics, the subjects are analyzed. Yeah. So I think this is the this is the future. The application of this methodology or these concepts to the assembly of systems in general, to the assembly of systems, I think this has a nice future. Yeah. To understand why the assembly is done in one way or not in other, who is really at the origin of the assembly, because the electric field lines are not only how a single molecule is filled by the other ones in the space, but when you put in the assembly, the connection between the interaction sites is directly pointed by the electric field lines from the electrostatic point of view.
Okay, as we do not have more questions now nor comments, so let us thank Enrique once again for this lecture and discussion.